All right, can you see my screen? All right, let's get started. Some reason there's a random oh, you can't see it, but there's a random goose flying around on my notability pad. It's a rooster or something, I don't know. So today I just thought we'd go over some basic principles of glycolysis, general overview, where we're going, and some individual steps to help you memorize the 10 different steps. I would say it's better 10 transformations because especially with the aldol reaction and the phosphorylation, it's really two or more steps rather than just the one. But you can think of it as one synthetic step. So, where are we at? So we've seen in class the total stage of catabolism, not cannibalism. So that would be fun too. Where carbohydrate or where glycolysis fits in is where we break down the molecule glucose. Either we convert it, go away, goose. We convert, let's see, what am I trying to say? So glucose is really the main metabolic pathway because that produces or helps to produce all the other intermediates needed for other elements of the metabolic pathways. So the main point is that we take glucose, which is a 6 carbon unit, we break that down through via glycolysis into two 3 carbon units, otherwise known as pyruvate, and that pyruvate gets converted into acetyl-CoA. Now, the main points throughout all of the the catabolic pathways is we're producing energy molecules, more particularly in the form of NADH, FADH2, and ATP, or GTP if you're looking at the citric acid cycle. This, let's see, where's my highlighter? You'll notice it's in color today. ATP and GTP we can use for energy directly. NADH and FADH2 we can use for energy later on, but this is all going to go into the electron transport chain, the ETC, and that's where the bulk of our energy is going to come from. So with that, let's just take a look. Let's do this worksheet really quick. Take take a couple minutes and work on it by yourself, and then we'll go through it. And after that, we'll point out some key elements. So you got glucose activation, sugar splitting, and oxidation, and formation of ATP. You don't know, that's fine, just do your best. Michael. All right, we'll go for one more minute and then we'll work on this first half together. All right, you ready? So let's go with the molecules on. Let's fill out A, B, and C first. Those are the molecules. Those are the intermediates that we're going to form. So the first thing we start with is obviously glucose. And by the way, there's a key at the end of this, but this light circle is oxygen, this darker circle is carbon, and this bigger one right here is just the inorganic phosphate group. The first thing that happens in glycolysis is what? It gets phosphorylated to form glucose to glucose 6 phosphate. And what happens after that is it undergoes isomerization to form which molecule? Fructose 1,6 bisphosphate. This transformation right here is probably the trickiest one because you go from having a 6-membered ring to having a 5-membered ring. But this is important for the sugar splitting step because it puts it in a place where we can evenly cut the molecule and get even distribution of both phosphate groups. So during the first 4 steps of glycolysis, what's transferred? We transfer 2 phosphate groups. And I'm not going to write small enough. 2 phosphate groups are transferred to glucose or the glucose 6 phosphate via phosphorylation. And this is where your ATP comes in. This highly energized molecule right here, because it's a triphosphate, it's the phosphoanhydride. We're going from a phosphoanhydride to a phosphoester on the glucose. And remember that this is level 1 electrophile and this is a level 2 electrophile. So by doing that, we're going downhill in energy, and that's what's providing the kickstart for this reaction. Let's see, via phosphorylation, where ADP is converted, ATP is converted to what? ADP. Yep, that's the easiest part of glycolysis. The end product of this is fructose 1,6 bisphosphate. Now this here is the tricky part because all to this point, it's all been one continuous chain, just kind of shifting around, and we've added a couple phosphate groups onto the end. Now this, where fructose 1,6 bisphosphate gets split into 2 fragments. And what are those 2 fragments? Dihydroxyacetone phosphate, DHAP, and glyceraldehyde 3-phosphate. Now you have to be mindful that the glycerol, this G3P will need to get converted into dihydroxyacetone phosphate. Or no, it's the other way around. Sorry about that. We have to convert DHAP into glyceraldehyde 3-phosphate in order to perform the rest of glycolysis. DHAP gets converted into glyceraldehyde 3-phosphate. All right, now look at this half. So now this is the second phase, which is the energy payoff. And the key point is we have oxidation to form NADH. I'll just fill that in for you from NAD plus, and we generate a molecule of ATP. Actually, two molecules of ATP. Right now. All right, you done, or do you want more time to work on it? Yes, no. All right. So this is okay. So this is the payoff phase. And you have to keep into account that because we generated two 3-carbon units, we really repeat this phase twice. I think a lot of people are probably going to forget that because you learn it doing just the one molecule of glyceraldehyde 3-phosphate, but it happens to both fragments. So the first thing that happens is that both of the molecules of glyceraldehyde 3-phosphate get oxidized using NAD plus. So NAD plus, let me put this down here. So NAD plus and FAD will always be your oxidizers. And their reduced form, NADH and FADH2, will be your reducers. Now, how are you going to remember this? Well, remember back a long, long time ago where we did reduction chemistry with hydrides. Remember this? Where we took sodium borohydride, reduced an ester, and we achieved an alcohol. This was what? A reduction. So NADH and FADH2 each contain an equivalent of a hydride ion. The hydride ion is the active reducing agent. So that's how I remember that NADH and FADH2 are both they give the hydride, so they're the reducing agents, and their counterparts are just the opposite, oxidizers. So let's see. Pen. Become oxidized using NAD plus, which becomes NADH. This process releases energy, which is used to attach what? Phosphates, making them 1,3-bisphosphoglycerate. And that's what this molecule is right here. 1,3-bisphosphoglycerate. All right. So that's really all preparing for the final step where we're getting down to pyruvate and where we get the last. Well, this is the actual payoff phase because this step right here is just compensating for the ATP that we lost beforehand. It's the conversion of phosphoenolpyruvate to pyruvate that gets us back our net of our gain of two ATP molecules. Imagine if God created the universe and it's just like, oh, I got the same number of ATP molecules in as I got out. So during the last four steps of glycolysis, the phosphate groups of the molecule are transferred to a DP, creating what? ATP. This is done via the process of substrate level phosphorylation. And of course, there is an enzyme for every one of these steps, usually just to shuttle protons around as acids or bases. But I want you to notice something with this oversimplified diagram. So you know that the conservation of mass is a real thing, right? At least when working in organic chemistry, or unless you're creating something like in the celestial kingdom. So right, we have six carbons to start out with. We end with six carbons. Really, the only thing that's happening is they're shifting around what's attached to those carbons. So with terpenes, we saw a lot of skeletal rearrangement with the carbocations. But here, the carbons all stay in the same relative orientation. So what do we mean by that? What did we do? What was the first thing we did whenever we did retrosynthesis? Figure out what our starting materials are. Yes, count your many carbons. Name them one by one. So let's just write those out really quick to show you how that works. So 1, 2, 3, 4, 5, 6. I'm leaving out the oxygen, just counting the carbons. 1, 2, 3, 4, 5, 6. Then you can see that this just gets bumped up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then it just goes the rest of the way. 1, 2, 3. Also 4, 5, 6. 1, 2, 3, 4, 5, 6. Mhm. Does that make sense right there? Okay. So now we look at the other individual steps, and we can highlight that again here just for completeness. I know this is in the completely gay Haworth projections, but this is the only thing I could find online that could forthrightly summarize everything. So again, let's just number the carbons. 1, 2, 3, 4, 5, 6. And to keep it consistent, I'm just going to start highlighting them like this the rest of the way. Looks like I need a smaller highlighter. There, that's better. There's my highlighter there. Do 1, 2, 3, and then we'll do 4, 5, 6. Then it's 1, 2, 3. Oh, whoops, back to orange. 4, 5, 6. One, two, whoops, there's the third one. 1, 2, 3, 4, 5, 6. And the right side gets converted into glyceraldehyde 3-phosphate. So that's 1, 2, 3. And the left is 4, 5, 6. And then throughout the rest of this is just an overlap between the two. Yes.
How exactly does sugar splitting occur?
How does it occur? All right. So I'm glad you asked that. So let's see. So this happens through so first of all these reactions you have seen before. They're just like Claisian condensations, aldol chemistry, isomerization, phosphorylation, which is basically nucleophilic acyl substitution. So none of this that we're going through is really, I mean, it's new, but it's not new chemistry. We've already seen all of the concepts. So since you've asked about that, let's talk about the conversion of phospho 1,6 bisphosphate to dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. So let me just copy that down really quick. And let me just write down the products. So we have glyceraldehyde 3-phosphate, which is, what does that look like?
Yes, it's the carbon between the OH and the ketone. That just leaves a proton attack.
Pretty much, yeah. Do you still want me to go over the, okay. Let's see. Any other questions about how that works? Yes.
So the irreversible steps, is that when we're going from ATP to ADP? Those the only two that are irreversible?
Let's see, where is it? Yeah. It's it's the 3 steps. So this one right here, when we activate it, when we phosphorylate the 2 sugars, so glucose to glucose 6-phosphate and glucose and bisphosphate. And finally, this last one, phosphoenolpyruvate to pyruvate. Those are the only steps in glycolysis that are truly irreversible. Yeah. Hmm. For the last step? No. So it's the this is exactly what Andrew was just asking. So when we add a phosphate group, so it has to do with the type of no, electrophiles that we're using. So when we're adding a phosphate group to either glucose or fructose 1 bisphosphate, or going from a level 1 phosphoanhydride to a level 2 phosphoester. So those two steps are irreversible. But when we're doing the splitting, yes, we do get a molecule of energy out, but the levels of electrophiles are comparable, level 2 and level 2. So we're not, the energy is, there's no such thing as zero energy, but it's low enough that it can easily go back and forth. And the other step is the same thing, phosphoenolpyruvate to pyruvate. Again, it's going from a phosphoanhydride to a phosphoester, level 1 to level 2. Steps 1, first step, 3, yeah, 1, 3, and 10, those are the steps of glycolysis that are irreversible. In fact, when we get into gluconeogenesis, the body has to do a roundabout way to get back to its starting point. Gluconeogenesis uses all the same molecules, but it has to go through a different route because of that energy difference in those irreversible steps are so large. Okay. So here I have for you a nice table that classifies what the enzyme is, the reactants and the products, and the reaction type. So this phosphorylation, whoops, what is this? It's just a nucleophilic acyl substitution. It's the same concept where I've taken a nucleophile and added it to the carbonyl in order to make our tetrahedral intermediate. But here you have to be a little bit careful. It's all the same chemistry, except when you have a phosphate group, O minus, O minus, nucleophile, and of course we have some leaving group off of there. Always, 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 just like we do with the carbonyl equivalent, we actually go through a pentavalent intermediate. Pentavalent because, whoops, I did not write that very well. Let me just move this over. So it never ever, it doesn't do a substitution directly where it just attaches and then the leaving group comes off. It attaches the phosphorus, the pi electrons hop back onto the oxygen, and then those pi electrons come back down, or the lone pair comes back down to form the pi bond, and the leaving group comes off. I'm pretty sure something like that is going to show up on the exam, where where instead of seeing that directly, it'll be like there's a labeled carbon 13 or a phosphorus 15, something like that. That's actually how they figure out how this stuff works. They label the specific carbon units and then just follow it with NMR. Remember NMR? Okay. Phosphorylation, step 3. It's also in here, step 6, and of course, step 10. But remember, step 6 is not irreversible. So we've also seen isomerization in two different contexts. First, when we go from the glucose 6-phosphate to the fructose 6-phosphate, and the DHAP to the glyceraldehyde 3-phosphate. Now, really, all these is just enol chemistry followed by tautomerization. Enol plus tautomerization. And so strictly speaking, any other isomerization steps? Well, there's this one, but it's kind of a weird one, so we're just gonna ignore it. These steps in particular involve multiple intermediates because you have to go through the enol or the keto equivalent and then convert it via tautomerization to the other one. So it's usually like 3 or 4 steps. One total transformation, but it has to go through that intermediate. So aldolase. So this is just a reverse aldol, which is basically taking our enolate. We've seen that before. An enolate which we generate with a base such as sodium hydroxide, like this, and then add it to another equivalent of that molecule to form the beta hydroxy ketone or the alpha beta unsaturated ketone or ester. This is just the reverse of that. This does look a little bit finicky because you're used to seeing the enolate being the nucleophile, and that's true most of the time. But this is different because now the enolate, whoops, I didn't meant to highlight that. The enolate in this step is now the electrophile. And why can it act as an electrophile? Because we can resonate that lone pair of electrons into the carbon. See any other steps? Enol, tautomerization, phosphorylation, redox. Did that one. Dehydration we've done before. That's really more of a 351 reaction, but that's just taking off the alcohol and converting it into an alkene.
I'll talk to you about dinner. I don't.
Yes? Hello?
Sorry, my
Sorry, my
microphone turned
microphone
on.
turned on. Okay. Ooh. I was like, oh no, who's there? All right. So here are a couple of problems that you wanted to focus on. So where do the labeled atoms, and remember, let's just count the carbons, 1, 2, 3, 4, 5, 6. Where do the labeled atoms of glucose end up when glucose is catalyzed to, or catabolized, not cannibalized, to each compound? Let's see, this is acetyl-CoA. And this is the one right before pyruvate, which is what? That's lactate. Let me just confirm that lactate molecule. Yep, that's well, it's yeah, it's lactate. And this final one is, what is that one? 2-phosphoglycerate. Is that right? No. See, carboxyl. Yeah, it's 2-phosphoglycerate. All right, take a few minutes and chew on that for a bit. All right, looks like most of you are done working on it. All right, so again, we have to retrace our steps back to see where the labeled carbons are. So let's see, how do I want to do this? So before we do the glucose, we do the fructose 1,6. Before we split it up into 2, 3 carbon species, we're at fructose 1,6. Sorry, I'm doing it in the Hayworth projection. I don't know. Let's see. And so splitting it down the middle. So the 1, 2, 3 carbons on the right, this is broken up into dihydroxyacetone phosphate, which looks like this, and I'm just going to abbreviate with P O H. Whoops, that's carbonyl. Let's see. Alcohol, CH2, carbonyl, CH2. And then the other side gets converted into glyceraldehyde 3 phosphate, which is OCH2, OH, and the aldehyde. So this is 1, 2, 3, and this is 4, 5, and 6. So 2-phosphoglycerate, where does that come in? That comes in the very end, glycerol. Yep. So remember, going back to what I said earlier, the carbon chain does not rearrange. Everything, except for the splitting step, everything stays in the same relative orientation. So with that in mind, we have 1, 2, 3. So 2-phosphoglycerate is also just our 1, 2, and 3, or our 4, 5, and 6, because DHAP gets converted into glyceraldehyde 3 phosphate. So let's see, this blue carbon was number 1. So it's going to end up being this, yeah. This is going to end up just being that one. Carbon 1. Let's see. Or would be carbon 4, depending on if you're Q instead. Let's see. And that's carbon 6, or that's carbon 5. So that would end up, this one would end up right here. Does that make sense? The way I've annotated it. Okay. 4, 5, 6. All right, now we go to lactate. So lactate is actually, it's not strictly part of glycolysis. It's a step off of glycolysis when we have no oxygen. And it's actually just the reduced form of pyruvate. How can you tell that? Because this is the ketone and this is the alcohol. But we look at the pyruvate molecule, and that's just the same labeling we've had before, where it's 1, 2, 3, or it's 4, 5, and 6. So let's see. That orange molecule was on carbon 1. So this is where orange highlight. And then the red highlighted carbon was number 5. So then it's just going to end up, whoops, it's right here. So here's the orange highlight. And then the other carbon will be the red highlight. Would those show up in the same molecule? No, they wouldn't. Different molecules. I feel like I should just draw that out for clarity. So, 2-phosphoglycerate. OH, H. Let me copy this. Highlighted blue there. Oh, sorry, it's blue. Blue highlight. So carbon 1. So in part A, let me label this as A. So the carbon 1 in A would show up right there. And then the red carbon would show up right here. So they still keep the same relative positions, but they would not both be labeled in the same molecule. Same with lactate. I'll just redraw that out for clarification. So this would be the blue one, would be the blue one right here. And then the second carbon would be the red one right there. Does that make sense? But I'm keeping track of the carbon. The reason why I thought you were going to get confused is because I was labeling the same molecule, but since they're on 2 different chains, they show up in 2 different molecules. Still the same pathway and tracing, but different locations. Yes, Taryn? It is. That is the end carbon right there. Oh, you mean this end? Because this is the end that's getting oxidized. So that let's see. Let's go back up here.
In the textbook, it has like red carbon, the same as the liquid, and it's like blue paper.
All right, let me check. So pyruvate 1, 2, 3, 4, 5, 6. No, I believe that would be the case. Let me check something. 2, 3. No, you're right. It is on the other carbon. Yeah. Yes. Yeah, that makes sense because this is the this number one atom has the two oxygens attached to it, and the pyruvate also has those three oxygens attached to it. All right. Final one, acetyl-CoA. So that is where we take pyruvate. And convert it into the acetyl-CoA, which is this. This is carbons 2 and 3. So let's see. We already determined what it would be for lactate. So yeah, the red carbon would be there because that's the equivalent of 5 and 6. No, that's blue. But the other one would not be there. Wait. Yeah. 5 and 6, 5 and 6, 2 and 3, 2 and 3. Yeah. But there is no second highlight. That this first carbon right here, that's actually going to come off as carbon dioxide. So yeah. So with the 2-phosphoglycerate and lactate, we get two separately labeled molecules that are the same, but the final one we get two different molecules that are labeled. Yes, Michael?
Does this mean that one would be with 6, 2 with 5, and 3 with 4?
What do you mean?
Like, I guess when dihydroxyacid phosphate gets turned into G3P, the one carbon is in the position of the 6 carbon.
Yes.
So it's not.
Yeah, you're right. I got the numbering backwards.
So it's yeah.
Mm-hmm. All right. Hope that was helpful. That's it for recitation today. We actually only have one more recitation after this, and then the final.
Oh, no. That mean next time is more of like a final review type deal?
Uh, I guess so, yes.